All right, we're having a look at worked example 9.1c. It's page 252 of our textbook. That's the New Century Physics for Queensland. So we've got a battery here with 12 volts, and the current's going to come around here through this resistor, down, and here it's going to split into two parallel parts. Both of these have got 10 ohms of resistance, so that means our current will actually split equally because they're exactly the same. Then the current comes back together and comes up here and around and returns to the negative electrode. Remember that current in conventional terms goes in the opposite direction to what it actually goes. So in a circuit diagram, you think the current goes this way. We know now that it's electrons going the other way, but when these sorts of things were first developed, they thought they were positive charges, so they moved the way that a positive charge would go in your diagram. Okay, so we've got to find out our current here and the voltage across here, the voltage drop, because as the electrons move through this parallel part here, through any resistance, they lose energy, and you measure the voltage drop across circuit components. So we're measuring it across here. It's the same energy loss or the same voltage drop in either arm. It's the same. So it wouldn't matter if these were different numbers. In this one, it's obviously going to be the same because the resistances are the same. But it wouldn't matter if they were different resistors. The current would split so that more current went through a smaller resistance and less through a higher, and when you multiply the two together, you end up with the same voltage. So the first thing I want to do is replace this parallel component with a single resistance, and then I'll be able to add that to that one and find out the total resistance of the circuit. So I'm going to get this part of the circuit here, and I want to know what the resistance for it is. So it's parallel, so I'm going to use the rule 1 on R equals 1 on R1 plus 1 on R2. Right, so we have got 1 on 10 plus 1 on 10. So that's 1 on R. So we're going to flip both sides to get the reciprocal, to get R. It will be 10 over 2. So the resistance of that part there is 5 ohms. So that means we could replace that section with a 5 ohm resistor. So then we would have our circuit would be like this then, wouldn't it? Oops, forgot a little bit. Here we go. So we would have 20 ohms and 5 ohms. And once it's in series like that, the rule's much easier. It's just the total resistance is equal to the resistance of the individual components. So we'd have 20 plus 5, 25. Okay, so now we know the total resistance of the circuit is 25. We've got the voltage given to us, so we can just use V equals IR or Ohm's law. V equals IR. So 12, 25. I is going to divide both sides by 25. 12 over 25, which is 0.48. And that would be measured in amps. Now, the textbook example changes it to milliamps. I think that's just unnecessary extra work because you need everything in amps, that's the SI unit, to do anything with it anyway. So you'd only be converting it to milliamps and then converting it back. So just leave it in amps, that'll be fine. Okay, so that means that was the voltage. That was the total resistance. This is the current, that total amount of current that can flow in this circuit. So that's what this ammeter here is going to show us. It's going to be 0.48 amps. Okay, so that's 0.48 amps. When it comes through the parallel part of the circuit, it was going to split evenly. So we know it's going to be 0.24 through this one and 0.24 through this part. We know that because these resistances are the same, so the current will split equally. So current splits equally. Equally. Therefore, ammeter 2 is going to be 0.24 amps. So the voltage drop across here is the same across this one as across that one. So we'll just use V equals IR again. 0.24 times 10, 2.4 volts. That's it. So this voltmeter here is going to read 2.4 volts.